Now welcome to lecture, I think 3, Calc 3, Math 150. And so what I want to do today is this is going to be our first day where we really have flipped the course. And so I've had a couple of you send me some comments about things that you want covered. If you haven't done so, I strongly encourage you to do so for the future, because this will be a chance for you to have some control over what's going on. If I wanted to be cruel or inquisitive, I could say close your books right now, take out a piece of paper, and write down what is the law of cosines, and write down what is the formula for the determinant of a 2x2 matrix. I am deliberately not looking in the audience to see who is happy and who is not, but if you are one of the people who is not happy, that means you are not prepared for today's class. If you're like, yeah, game on, then you are doing a good job of reading what you're supposed to and being ready. And this means that we can save class time, and rather than going through a lot of the standard stuff, I now have time to talk about either more applications or more examples or more problems. All right, so the first question that somebody had asked was from homework number 1. What is wrong with the following argument? Somebody left a good chalk. All right, so I actually have a stash from Michigan of good colored chalk. And so that's for really special lectures. It erases very nicely. You learn a lot more from a proof that fails, from an attempt that fails, than you do from something that works. And so the question is, what is wrong with this proof? And so the question here was, you have the parabola 16y equals x squared, or if you want y equals 1/16 x squared. So it's going to look something like this. And when x equals 0, you know y equals 0. If I wanted to, I could put down a few points and have some nice sense of what's going on. And the question is, we want to find which point on the parabola is closest to the point 0, 5. So here is 0, 5. Any natural candidates? Okay, so I had deliberately left my cell phone on, and now it is off. So which one was the first candidate? 0, 0, that's a very natural candidate. What are other natural candidates? Those are possibilities.
The x value, or the y value where x equals 5.
Yeah, the y value where x equals 5?
Or the x value where y equals 5.
The x value where y equals 5 is, these would be natural places to try. Maybe coming down over here, where maybe you intersect at a right angle, where the line from the point to the tangent line is perpendicular. You just try to think geometrically, are there any natural points that would be worth investigating? And then even if you can't solve the problem, if you have a finite set of points to check, maybe I can get at least best of the possible ones here. And so the argument they say is the following: there is no shortest point. Now, what I like about this argument is your spider sense should immediately be tingling. This is absurd. There's got to be a closest point, because as I go higher and higher up, I'm clearly getting further and further away. So if I just look at all the points in through here, one of them is going to be closest. And if I go far enough away, all these points are more than 5 units away. So there is clearly a closest point. So it's nice to know that what I'm about to show you has to have a mistake somewhere. We are not always this lucky to know that there is a mistake. And so the argument goes as follows. Since 16y equals y squared, the distance squared is equal to, so let's say our point over here is xy, so it's going to be y minus 5 squared plus x minus 0 squared. And is this how they want to do it? Or are they saying 6? Okay. So this is going to give us y minus 5 squared. Now x squared is just 1/16. It's just 16y squared.
Just 16y.
Oh, sorry, 16y. Thank you. And we know y is going to be greater than or equal to 0. And we can try to see where is the smallest. Now, I'm looking at distance squared and not distance. If I minimize distance squared, is that the same as minimizing distance? Yeah. Distance squared is much nicer because it doesn't involve the square root. It makes the derivatives a lot easier. What's nice is this is a class of multivariable calculus, but we're just doing one variable calculus right now. We've replaced a function of two variables, x and y, with a function of just one variable. So we can calculate the derivative of, say, a distance squared function with respect to y. That'll be 2y minus 5 plus 16. And we set it equal to 0 to find the critical point. And so what will the critical point be? Yep, that's what I get as well. So we get y equals negative 3. Well, there's no x that corresponds to y equals negative 3 because y is equal to 1/16 x squared. So we're done.
No, we need to check the boundaries.
We need to check the boundaries. Right? It is not enough to check, we'll see if this works, to check the critical points. Tell me where I am traveling at the fastest. Does anybody have any friends in the classroom over there?
Are you going to slam into
Yes.
the wall?
Ready? Where's my speed fastest? Okay. Oh, it did not turn well. Yeah, now it turns. Okay. The point of that, in addition to waking up whoever's there, is to really drive home the point for the rest of your life that you need to check boundary points. It's not enough to just check the critical points. What are the boundary points for this? Right. And when you look at this, you might think it's x going from minus infinity to infinity, but really, by the symmetry, I'm really just looking at it, y goes from 0 to infinity. And so when I look at it like that, my endpoints are y equals 0 and y equals infinity. When I take y equals 0, that's going to be the minimum distance. So it's actually coming straight down like this. And in fact, if you notice geometrically, it is perpendicular over there. Whether or not that has any meaning, I don't know. So a lot of good stuff in this problem. So way to review some of the stuff from Calc 1, Calc 2, applications of derivatives and critical points, and how easy it is to forget a condition. That when you are going to use a theorem, you have to make sure all the conditions of the theorem are met. All right, any other questions on this? Okay. All right, so the next thing that people had asked about was induction. How many of you have seen proofs by induction before? One person. Do I have a volunteer for today's lecture? Oh. Do you accept or do you want to push back to her?
You're going.
Sure.
Okay, do you have your ID on you?
Yeah.
Okay. And you're willing to take it out? All right, I need to see this and make sure that you are a valid William student. I was a little bit worried that you're taking off your glasses. Were you getting ready to run? And I want to prove that everybody's named Cooper.
Everyone's named Cooper?
Yeah.
Oh.
Okay. But do you have a problem with that, Cooper?
Yeah, I didn't know you.
You see, you immediately said yes. You immediately said yes. So when I called you Cooper, you didn't flinch. So induction is one of the most useful techniques we have in all of mathematics. It's a way to prove a variety of statements. So we start off with some statement Pn, and we show P0 is true, or sometimes you start with P1, and then you show Pn true implies Pn plus 1 is true. And once you do that, you now know P is true for every integer. Sometimes instead of starting with 0, you start with 1, and then you just, so it's always true for all integers from 1 onward. Why is this true? Well, I know P1 is true, and I know P1 implies P2, so what can I conclude? Oh, sorry, we're starting off with P0. And then we know Pn implies Pn plus 1. Let's take n equals 0. And then that gives us P0 implies P1. So what can we now conclude? P1. We now know P1 is true. We now come back to a general statement. Pn implies Pn plus 1 is true. What value do we take for n now?
1.
1. And we now have P1 implies P2 is true. So what can I now conclude? P2. And now it's the shampoo method of mathematics. What are the directions of shampoo?
Oh, wash, rinse, repeat.
Oh, I always said lather. Oh, you just keep repeating again and again and again. Now you know P2 is true, then you prove P3, P4, P5, and so on and so on and so on. So this is proof by induction. So for instance, maybe I'll have my statement, I'll take one of the, no, that one's done. I'll do the boring one, or maybe I'll do a more interesting one later. 1, well, let's do 0. 0 plus 1 plus 2, let's go all the way up to plus n is equal to n plus 1 over 2. How many of you have seen that statement? Okay, so since a lot of you have seen that, I'm not going to prove that by induction. You can prove it by induction. The simplest way is to actually just write the numbers backwards. And then you get 0 plus n is n, 1 plus n minus 1 is n. So I'll leave that as an exercise for you to think about. Since you've all seen that, let's do a different statement. Let's do Pn is 0 squared plus 1 squared plus 2 squared plus n squared, I believe is n plus 1, 2n plus 1 over 6. This is where it might be better to be in section 2 than section 1, because for section 2 I will clearly know what the correct statement is. I'm not sure though. I've been traveling a lot, had a lot of meetings, this might be wrong. What should I do? Well, okay, prove it, that would be great. But I might be trying to prove the wrong thing. If I have the wrong formula and I try to do things by induction, I'm going to have trouble.
Can we check it?
Yeah, let's check it. Yeah. Let's check P0. Does 0 squared equal 0? Yes. Not a problem. Let's do P1. So does 1 equal 1 times 2 times 3 over 6? Yes, it does. Let's check 2. 1 squared plus 2 squared is 5. Does that equal 2 times 3? That cancels that. Perfect. It equals 5. Should we continue checking? You could check a few more just in case you're worried. We'll assume that we checked a few more and they all seem to work. So at this point, we're getting pretty confident that we have the right formula. And now we want to prove it by induction. So this would be the base case. You don't have to just do the 0 step. You could do a few more just to make sure and just to really get a sense of what's going on. This is one of the most important sums you've never seen. You should have seen this in your calculus classes. How many of you have seen this in integration theory? In integration theory. I'm sorry?
I think the could show it kind of like close to median sums.
Yes. You should be seeing it for Riemann sums. Yes.
P2, that's supposed to be a 4, right?
No, because we're squaring things. 1 squared plus 2 squared is 5.
Okay. Never mind.
Yep, no problem. No problem. All right, so now we want to prove this by induction. So we've done the base case. We've shown P0 is true. Now we want to prove the inductive step. We want to assume it's true for n and show it's true for n plus 1. So we get to assume Pn is true. So we can assume 0 squared plus 1 squared plus n squared is n plus 1, 2n plus 1 over 6. Now we want to show that Pn plus 1 is true. So let's consider Pn plus 1. That's 0 squared plus 1 squared plus n squared plus n plus 1 squared. What do we know about part of this sum? I'm sorry?
N squared plus n plus 1.
Yeah, by inductive assumption, we know what that is. This is just n plus 1, 2n plus 1 over 6 plus n plus 1 squared. I'm going to write that as n plus 1 times 6n plus 6 over 6. And I'm doing that because I have a sense of what's coming next. I want to combine them. I have an n plus 1 over here. I have an n plus 1 squared. I can pull out the n plus 1. I have a denominator of 6. And so I will let you do the algebra. And after some algebra, you will get that it's n plus 1 times n plus 2 times 2n plus 3 over 6, which is exactly what you need. So I will let you do that algebra. It's not enlightening. All you have to do is just add these, expand this out, and see that they're the same. There's a lot I can say about induction. We may talk about it more later. It's one of our most common proof techniques. It works much better when you know what you're trying to prove. If you don't know what you're trying to prove, well, how am I supposed to do the argument? There are ways to find the formulas. One of the things is this should be reminding you of calculus. This looks like integrating the function x squared from 0 to n. And if you integrate the function x squared, what's the antiderivative of x squared? 1/3 x cubed. And if you look at this, the main term is going to be a 2n cubed over 6 or 1/3 n cubed. So this is really looking like what's going on. I do not want to go into extensive detail right now. What I will just quickly say is that when you're doing the fundamental theorem of calculus, bless you, this is one of the most important results in Calc 1, Calc 2. You don't get called fundamental lightly. So if I give you fundamental theorem of calculus, let's say f continuous, differentiable, f prime is continuous. So here's some interval a, b, here's some function f. Big F prime is little f, then the area under the curve from a to b is the antiderivative at b minus the antiderivative at a. And this is area. If you do not say area, you make me upset. It is at the level of rooting for the New York Yankees in this class. Okay? That is how bad it is. Because if you don't say area, this is just a definition. What do we mean by this? We mean the area under the curve. The content of the fundamental theorem of calculus is that the area under the curve is given by the antiderivative at b minus the antiderivative at a. How many of you could prove the fundamental theorem of calculus right now? Okay, so we will prove this later in the semester. We will prove why the fundamental theorem of calculus is true. If you can't prove it, what can you do if you can't prove something, if you want to see if it's true or reasonable? Check it. So what's the simplest function you could take for little f of x?
X squared.
No, come on. No.
0.
Yes. Right? Do not be afraid to be a smartass with questions like this. Start off with the easiest thing possible. Let me take the function that's identically 0. All right, that's really degenerate. Can we do a little bit better than just the function that's identically 0?
1.
1, or just any constant. So 1 would be great. And so if you try the function that's identically 1, what happens? So if we try little f of x is 1, the antiderivative is x. Oh boy, right? What shape have we just found the area under? A rectangle. It's great. We will verify the fundamental theorem of calculus, but this is not an achievement, right? We know areas of rectangles. What's the next simplest function we could try? So if we try f of x equals x, what's the antiderivative?
1/2 x squared.
So what kind of shape is this going to be? A triangle. And yes, we can calculate it directly, but are you excited about proving the area of a triangle using calculus? This is the classic example of the elephant gun approach. Wow. So we developed all of this calculus machinery to find areas of triangles and rectangles. The first non-trivial example is f of x is x squared, and the antiderivative is 1/3 x cubed, is our parabola. And now we finally have a situation where we do not immediately know the answer. I believe the ancient Greeks did have a formula for the area of parabolas, but this is not something that is immediately obvious. And that's where we use the sum we just proved by induction, to find the area under the parabola using the Riemann sums, using the upper and the lower sums. It's the first non-trivial test of the fundamental theorem of calculus. And now we begin to think, oh, there might be something to this. All right. Does anybody have any questions on what we've done so far? Yes, Cooper.
So if you have f of x equals 0,
Yes?
what's the antiderivative?
The antiderivative would just be 0.
Still?
Still.
Okay.
Because you're 0 everywhere. Right? So if f of x equals 0, your function has to be identically 0. Think of it as your speed is always 0. So your distance from home is always 0. Now you seem to flinch when I called on you. I don't know. I mean, I haven't known you that long. Maybe it's a little early in the semester to be calling you by your first name.
Oh, I think I was just taken aback that you called on me. Yeah.
Okay, but everything is okay, Cooper?
Yeah.
Okay.
For sure.
Okay. Do people want to prove that everybody is named Cooper? Okay. Pn is any set of n people all have the same name. So we'll actually only prove that everybody in the world has the same name. But since we know that somebody in the world is named Cooper, we now know everybody in the world is named Cooper. That's why it's so important that there's at least one known person. Okay, so the base case, if I have any group with just one person in it, does everybody in that group have the same name?
Yes.
Yes. Okay, this is the. All right, so now assume Pn. Let's prove Pn plus 1. So I apologize that my art is horrible. We'll do some like disco people. All right, so here people is 1, 2, 3, n plus 1. Any group of n people have the same name. Can somebody give me a good group of n people to look at?
This question?
Well, the classroom's not on the board. Here are my n plus 1 people. Somebody give me a group of n people.
Just like cut it off like between n and n.
Yeah, so if you look at these people here, they all have the same name. Somebody give me another group of n people.
10.
Well, you have to, I have n plus 1 people listed here. You have to give me a group of n people chosen from these n plus 1. So somebody said take the first n. What else could I take?
First three.
I'm sorry?
First three.
Well, I have to take n people. So I took the first n, and I excluded n plus 1. That was my group of n people. Can someone give me another group of n people?
2 to n plus 1.
Yeah, I could take the last n. And look at all the people in both groups. So because the groups have people in common, they all have the same name. So everybody is named Cooper.
I don't buy it.
What don't you agree with, Cooper?
Why are you laughing?
But that type of commonality doesn't prove that it's not, it's like comparing apples and oranges, even though they may all be in the same types of groups, it's not proving that.
All I'm saying is any group of n people all have the same name. I showed the base case is true. I've shown now here that if Pn is true, Pn plus 1 is true. Everyone has the same name.
But what if the original assumption is wrong?
Yeah.
But I proved it. In any group of one person, you're not going to have two names.
Yeah.
But you didn't prove it
But
in
in a group of two.
Ah! So what I've done here, when I drew a very large value of n. N is at least 3 or 4. If I took n equals 1, what does n plus 1 equal?
Two.
And so in that case, the two groups are disjoint, and there's nobody in common. So if you think of induction like a ladder or like a staircase, there's a missing step. If it was true for 2, then it would be true for everything. Well, that kind of makes sense. If every group of 2 people, everybody has the same name, then everybody's going to have the same name.
Because it counts.
Right, because you could basically do things through me. Anybody ever see the TV show Futurama by the creators of The Simpsons? Okay, there's an episode where the Harlem Globetrotters turn out to be really good at mathematics, and they are involved in a mind-swapping episode. And you can trade bodies with people, but you can never trade with somebody you've already traded with. And so the question is, how many moves does it take to get people back? And it's a function of how many people you have who haven't been involved in the game initially. And in fact, one of my colleagues and one of his students actually wrote a paper on this and got published and got to talk to some of the people about it. You want to be very, very careful about assumptions that you're making. The very first thing we did today was the fallacy. We assumed things. Over here, it's another assumption. When I draw it like this, I'm drawing it deliberately in a way to mislead you. I'm drawing it in a way to make you think, well, of course, the easy ones are the small cases. Let me look at a big case. I can similarly prove every number is a perfect square. Every integer is a perfect square. It's a similar bad proof. Okay? So it is possible that everybody is named Cooper. Does everyone agree that it is possible that everybody is named Cooper? Yes. Right? But only one person in this class turns out to be named Cooper. But you've got to be very careful. We haven't disproved that everybody's named Cooper. We've just shown that this is not a valid proof that everybody's named Cooper. I love Mark Twain. I love his witticisms. One of my favorites is, a cat that jumps on a lit stove will never jump on a lit stove again, nor will it jump on a cold one. For each experience in life, only extract the lesson you should. Be very careful about pulling out too much. Okay, so I will assume everybody is comfortable with laws of cosines and just what the statement is. This is one of the key ingredients. It's one of the biggest applications of dot products. So law of cosines. So if we have 2 vectors, P and Q, and some angle, then P dot Q is the length of P times the length of Q times the cosine of the angle between them. Sometimes we overload notation, and we'll just say P dot Q is the length of P, length of Q, times cosine theta PQ. I like to use the double values to remind myself that I'm talking about a vector. I like to put arrows to remind myself that I'm talking about a vector. When I do integration, I like to write x, the integral x goes from a to b, to remind myself frequently that I'm integrating with respect to x. In one variable, it's not really necessary, but when you have more variables, it's very useful to be able to just quickly glance down and see what's happening. What this tells us is that there is a relationship between the dot product and geometry. Now what's nice is, if I flip the order of the vectors, it's not going to change the dot product, and it's not going to change the cosine of the angle, because cosine of theta is the same as cosine of minus theta. So we do not have to worry about orientation. We do talk for the cross product how orientation matters. We often use the right-hand screw rule, apologies to the lefties. You do P cross Q, and your right thumb points in the direction of the cross product. It'll be a vector perpendicular to the two of them. The cross product really only exists in 3 dimensions. If you want, it can kind of exist in 2 dimensions by just pretending the third component is 0. And then P dot Q, this is just going to be P1 Q1 plus P and Qn. for most of what we're doing, it really makes no difference if we're doing things in 2 dimensions or n dimensions. The arguments are going to be very similar. One of the big differences is in determinants. It would be wonderful if you had taken linear algebra. Unfortunately, given that this class is a prereq for linear algebra, it is not reasonable to expect you to have taken linear algebra. Well, you've probably had unreasonable professors before, so why should this semester be any different, right? We are not going to do a lot of things with n-dimensional linear algebra because that is beyond the scope of this course as to what you're supposed to know. But 2 dimensions we can do. So determinants. So how many of you have seen determinants in high school? So determinants represent area, or in 3 dimensions they represent volume. And there's a great geometric meaning behind them. And so we will just define for matrix A, B, C, D, the determinant of that is going to be AD minus BC. There is a more involved formula for determinants of 3 by 3. I will write it A, B, C, D, E, F, G, H, I. This is just a mnemonic. It doesn't generalize to higher, but if you rewrite the first 2 columns, A, D, G, B, E, H, then if you go down diagonally and add these 3 with a plus sign, and then you go up here and subtract these 3 with a minus sign, then that is going to give you the determinant of that 3 by 3 matrix. So I'm not going to go through the details of that here. I want to try to explain to you what the determinant is geometrically. So again, I am trusting you to read the book. I am trusting you to watch the video. If there is a question about some of the stuff, you are supposed to let me know. This frees up class time to actually talk and give you a little bit more of a geometric explanation of what's going on for the determinant. What we're really doing in n dimensions is if I give you a determinant of an n by n matrix, you have n vectors. And those n vectors form an n-dimensional hyperparallel pipette or whatever you want to call it. Let's just stick to 2 and 3 dimensions. We can talk about a parallelogram. We can talk about a box. And so if I give you 2 vectors, A, B, C, D, here's the vector AB, here's the vector CD, and we can look at the parallelogram spanned by these 2. And the determinant is going to give the signed area of this. If I flip the order of these 2 vectors, the determinant is going to change by a factor of -1. And so we go through and we use the law of cosines to prove why this is the answer. Let's look at simpler matrices. I claim that the determinant is the volume of the parallelogram spanned by the vectors A, B, and C, D, generated by this. So what does that mean? It means I have T times the vector AB plus S times the vector CD, 0 less than equal to T less than equal to S less than equal, T comma S less than equal to 1. I can go anywhere I want along from here, from 0 all the way up to 1 full copy, and then I can go in this direction anywhere from 0 up to 1 full copy. And that's going to give me a parallelogram. What's the easiest vectors, or what's the easiest 2 by 2 matrix to look at to try to get a sense of what the determinant is? So what parallelogram would be really nice to work with?
A square.
A square, right? Or if you're willing to be a little bit more general than a square is good, but you could be a little bit more general than a square. And the work is not going to be harder. So, a rectangle. So if I go to a rectangle, that's not going to be too bad. And so if I look at, here's A comma 0, and then here's 0 comma D, the area is just A times D. And if I look at my, I have A, 0, 0, D, the determinant is going to be AD minus 0 times 0 is AD. Okay, so the determinant is giving the area in this case. This is a nice proof or justification justification is all about. This is a good justification that there might be something to it. Now let's try to tweak it a little bit. What I'm going to do now is I'm going to change, I'm still going to keep A0, but maybe I'll add a little bit to this vector. And so now, maybe here's A0, and now I'm going to add a little bit to this. And now, I'm going to have this as my parallelogram. What's the area of this parallelogram? Yeah, it's still base times height. So as a nice exercise, prove that the area of the parallelogram is base times height. So what this is basically saying is if I keep the base fixed and I keep the height fixed and I just slide this down, they're all going to have the same area. And so there's lots of ways you can try to prove this. One way is you can start dropping down heights over here. You can look at this whole big rectangle, and then you could subtract off those triangles over there, which are right triangles. So it's a nice exercise to try to prove this. Yes.
Could we just set up a matrix? Well, why is that point 0b? Why isn't it CD?
Oh no, sorry. The point right here is 0b.
Oh, but the vector.
The
CD.
vector over here would be the vector CD.
And since b is 0, can we just set up a matrix? A 2 by 2?
Yes, and so if we now look at the corresponding thing, it would be A0CD.
So it still holds true.
Right, and it's still going to hold true there. And so this is a little bit more of a proof that things are working out nicely. It's not a full proof that the determinant is the area. But what I'm hoping is that this gives you some more of a sense, some more of a justification. I don't want to go into the full proof. This is not a linear algebra class. But I want to try to give you a little bit of a sense of what's going on. So this is not a full justification. How many of you have seen formulas for ellipses?
Yes.
These are the conic sections are the most forgotten part of, I think, high school algebra, where you can write down the equation of an ellipse. And if I give you an ellipse like this, and this is A, this is B, it's x over A squared plus y over B squared equals 1. If I give you an ellipse that is not aligned with the coordinate axes, this is where you use four-letter words. Did anybody learn how to write down the equation of this? It's one line once you know linear algebra. Linear algebra is all about changing your coordinate system to whichever system is best for the problem at hand. Hopefully you've seen polar coordinates. Where are polar coordinates useful? Circles. When you have things with circular symmetry, radial symmetry, polar coordinates are wonderful. Over here for this ellipse, I don't want to use the standard xy axes. What coordinate system do I want to use?
The one that you can hold.
Yeah, I basically want to lean back like this. Right? And if I look in a coordinate system like this, where say this is u and this is v, in uv space, I can write it down exactly like this. So what linear algebra does is it teaches me how to move back and forth between things in x and y and things in u and v. That's a lot of what we're going to be doing later in the semester in Calc 3, is we're going to be looking at different coordinate systems and how to move back and forth. If we knew matrices, it would allow us to unify a lot of the presentation. Well, we can do a little bit, and we can justify a good chunk of what's going on. All right, so we've talked about defining 2 by 2 determinants, 3 by 3 determinants. The determinant is basically related to the area, but it's going to be a signed area. In 3 dimensions, it's going to be a volume. So what this tells us is that if I give you a matrix where the same row is repeated, then it should have determinant 0. Or if I have the same column repeated, it should have determinant 0, because the parallelogram is going to be degenerate. It's not going to be full. If I give you something in 3 dimensions, and the second well, let's say the third row is twice the first row minus 4 times the second row, it's not going to fill up three-dimensional space, and that should have volume 0. That the determinant should somehow measure the volume of what's going on, and if the things have a dependency, it's going to be 0. Because what's the volume of a piece of paper in three-dimensional space? 0. What's the area of a line on a plane? 0. When you're lower dimension, you have nothing like that. So one of the big things is the cross product. So we often use I hat, j hat, and k hat for a unit vector in the x, y, and z direction. I have mixed feelings about this notation. One of the problems with this notation is that, well, what if you start working in n-dimensional space? How are you going to do all the letters? So sometimes instead we use E1, E2, and so on and so on and so on. Sometimes we use a hat to denote that something has unit length. So you can just quickly look at it and have a sense of what's going on. So if I look at P cross Q, the way you calculate that is I hat, J hat, K hat, P1, P2, P3, Q1, Q2, Q3. You just have to do things very carefully. I hat, P1, Q1, J hat, P2, Q2. And so now I would have I hat, P2, Q3, and I'm going to deliberately leave a space. Then I would have J hat, P3, Q1, plus K hat, P1, P2, P1, Q2. Now I have the minus ones. I would have P2, Q1 with a K hat, so they would come down here. Then I would have Q2, P3 with an I hat, so minus P3, Q2. And then over here, the J hat would be P1, Q3. And if you notice, it goes 2, 3, 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. So in each one of them, the P is always first, followed by the Q. The orders change. So it goes 2, 3, 3, 1, 1, 2. It goes through cyclically. Memorize this. Or remember this expansion over here and derive it from this. So this is the definition of a cross product. You can define anything you want in mathematics. Most definitions are stupid and useless and are not going to help you. It turns out the cross product is exceptionally useful. It has a lot of geometric meaning. If we just look at this part over here, P1, Q2 minus P2, Q1, right? This is a determinant of a 2 by 2 matrix. In fact, all of these, you can look at determinants of 2 by 2 matrices. If you've ever seen expansion by minus, has anybody seen that? Okay. If you had seen it, that would be related to expansion by minus, absolutely fine. But this part over here, you can view this as a determinant. And you can use this as a way of getting what is the area of a parallelogram. Is I just take the vector P1, P2, 0, Q1, Q2, 0, and this part over here, that cross product. So it turns out that the magnitude of the cross product is the area of the parallelogram spanned by these two vectors. And it's always going to be in a direction that's perpendicular. So what does it mean to be in a direction that's perpendicular? So if I have two vectors, how can you tell if the two vectors are perpendicular? Is that someone's phone? Okay, I just want to make sure that it's not the recording system.
Can you repeat your question?
Sure, if you have two vectors, how can you tell if they're perpendicular?
Dot product?
Dot product is 0. So I think I mentioned in the notes that I can give you painful algebra to do. Well, painful might be a bad word. It's not going to excite you. Tedious. but straightforward, follow your nose. I claim P cross Q is perpendicular to P and to Q. How could you check and see if this is correct? Yes?
You can see if the dot product is
Yeah.
equal to 0.
So P dot P cross Q, just do this out, and you will get.
0.
Now, is this 0 the number or 0 the vector?
The vector.
The-
The number.
I've got a split decision here.
Well, I mean, it's the same thing. 'Cause
They're not the same thing. One is a number, one is a vector. The P cross Q is a vector. And the dot product of two vectors is that a vector or a number? It's a number. So this is 0 the number. Okay? This is completely follow your nose. Put in what the entries are for P and Q, calculate the cross product, then take the dot product. So you would be P1 times this, plus P2 times this, plus P3 times this, and then just show when the dust settles that it is 0. There may be an exam question related to proving a vector identity like this. None of them are hard, they're just time consuming. The interpretation is if I give you A dot B cross C, this is actually the volume of the hyperparallelogram spanned by A, B, and C. And there's a geometric interpretation to what's going on. We can do these calculations by brute force, and we can see that P cross Q gives us a vector perpendicular to P and Q. This is where three-dimensional space is wonderful. If I tell you I have a vector perpendicular to P and Q, and I'm in three-dimensional space, how many choices are left for its direction? Okay, why 2? It can go up and go down. So there's really one direction, but I have a choice of do I want to be pointing up or down. So I know I have to lie on this line. This is what's wonderful about 3 dimensions. If you have 2 directions and you're perpendicular to both of them, I know which direction you are. If I'm in 5-dimensional space and I give you 2 vectors and I say I'm perpendicular to both of them, well, there's still a lot left. All right, so this is a really good chance for you to assess how the class went. I did not cover everything that was in the video. And I wanted to use that time to talk about other things. So let me know, email me how things went. I will end with one of the applications of this is in electrodynamics, where you talk about the electric field and the magnetic field, and you look at E cross B, the electric field, or often C times the speed of light times the magnetic field. And this is the pointing vector. It points in the direction of propagation of electromagnetic radiation. And who watched the video? What is the punchline?
I don't remember.
Oh, it said his name is.
Yeah, the guy's name is pointing.
Oh, yeah.
So when the physics professor wrote this, and we're all freshmen, we all wrote P-O-I-N-T-I-N-G. No, the guy's name was pointing. This is how you know you're going to be remembered for what you're studying. You know, they can't change it when your name is pointing. I'm going to study something that points. Okay, so there's lots of applications of stuff like this. So if you haven't handed in homework, please do so. If you haven't taken a Girl Scout cookie and you want to grab one, please do so.